that all affects the energy performance. And just to give you an idea, this is in the UK, but a similar sort of example, but we use obviously a huge amount for heating in the UK. Energy is used for heating. So over 50% when we combine that with heating hot water as well. So clean systems is a starting point, as well as well-balanced, well-commissioned and well-controlled. Again, some anecdotal examples of what's been out there, but you can essentially lose 6% of energy performance in your system in a matter of a week if it hasn't been treated correctly. If you're in a hard water area, you can lose up to 7% just from really an eggshell layer of scale that might bake on your boiler heat exchanger as well. So there are, in the UK, we have CIBSE as well as ASHRAE, but there are some, again, anecdotal examples where they sort of talk about you can have a well-designed system, but if it's not maintained very well, it's not going to perform. And conversely, you can have a poorly designed system, but with some optimization, once it's up and running, you can really make a difference. So, and that really does apply when we think about water quality. So the water quality we're talking about really pertains to closed loop hydronic systems. So the types of systems we're talking about are chiller systems, condenser systems. These are closed loop condensers, so not your cooling tower open evaporative. And LPHW, so sort of, your usual sort of temperature around about, apologies there, I don't know why that's in metric, I should have changed that, but typically you're looking at around about sort of the 200 degrees Fahrenheit kind of temperature. And what we don't cover is anything above 200 degrees. It's typically your medium pressure hot water or medium temperature hot water and steam, etc. That's not really covered on what we're discussing. So what is a hydronic closed loop system? Essentially, it's a pressurized heat transfer system or circuit, which does not normally require makeup. A typical system, believe it or not, though, will lose around 5 to 10% of water in a year, which is actually a significant amount. And that's because we use various different materials and gaskets and so forth that we can't really create a true sealed system. They do make up water. And, some systems can lose much more. There's many older systems that you may have projects that you'll become involved in or have been involved in that are losing, tons and tons of water. The biggest or the most I've heard of, we were helping a client in the UK, a university. They were losing 30 ton of water a single day. They're now down to about 1 ton. So it's quite an improvement. But so yeah, and of course, when we're losing water, we're bringing in fresh water, and that's really where we add more problems as well. So a very, very simple schematic, but essentially we've got a circulation pump pushing water around either a boiler or a chiller, where we're either heating that water or cooling that water, and then we want to deliver that heating or that cooling, that energy into a space through either a radiator, a fan coil, or air handling and so forth. There are some older systems in the UK, not so sure in the US market, where you'd find a feed and expansion gravity system. Not ideal because obviously the system is open to atmosphere. But typically most systems are now pressurized with a pressure vessel and a pressurization, some form of a pressurization unit or an RPZ valve. So you'll have maybe a glycol fill unit that tops up your system, depending on where you are in the US or Canada, or you'll be straight off the mains water RPZ. But I mean, if you've got an RPZ makeup system, if you do have water leaks, generally, how do you know about it unless you've got some form of an alarm? But when we look at that schematic, I want you to imagine that if it's a heating system, and it's in the winter, think of it as a chemical reactor. And then when we shut it down in the summer, or if it's a chilled system, think of it as a microbiological incubator. That might be sounding rather dramatic there when I say that, but it's essentially sort of some good examples to keep in your mind when we move forward to think about what can happen in our pipework systems. So the objectives of treatment is to essentially maintain the system in a clean condition. We want to assist in maintaining system efficiency, really, really important, obviously, as well, particularly as we're looking at much more higher efficient types of systems, boilers, pumps, and so forth. They're only as good as not just the technology, but they're not designed for, if you like, pumping around sludge. Prolong the system life. So when we look at cradle to grave, we look at embodied carbon. Maintaining good life cycle is very important. And many systems, poor water quality, you could have a system that is, should be fit for say 25 years or more, we've seen systems within 18 months and huge lawsuits that have come from that because they have failed. We're literally within 18 months due to poor water quality. Oops, excuse me, wrong button. And the big one is avoid conflict and misunderstanding. So certainly projects, you know, a lot goes into, you know, the collaboration with architects and engineers and contractors and so forth. But the handover piece is always critical, getting it handed over on time and, you know, working within its design intent. And when that doesn't happen, yeah, you can start to really see some conflict and misunderstanding between different parties and potential litigation. So what does it look like? I'm just going to throw some photographs up here. This is kind of what it looks like. So top left, starting top left, what we can see here is the deposit of suspended solids and settable solids. So this is really where flow rates have reduced. So we don't have we're not meeting sort of the ASHRAE minimum flow rates requirement, you know, through a set size, a diameter size of pipe work. So that we're allowing for these fine particles to settle out, and that's what they can look like after a period of time. And of course, then we're impacting the volume of water and the flow rate that we can put through that piece of pipe, affecting our delta T. Pump seal failure in the middle. Generally, the quickest giveaway, have a pump seal failure. The words I've heard from many sales engineers and certainly contractors in the US is, you know, pump seal failure. They say it's bad pump seals. I mean, generally, pump manufacturers do not make bad pump seals. As you can see from that photograph there, they're simply not designed for such poor water quality. Otherwise, they'll be used for sort of effluent pumps or such. Of course, then on the right-hand side, we have blockages. And once we get to a blockage in our system, huge costs then come into getting to that pipe work, strip it out to change it. In terms of CapEx, not just OpEx cost of energy and so forth, but CapEx costs and life cycle, we could be replacing radiators much sooner than we should be. Time and time again, I hear and I see from, you know, estates technicians, you know, universities and hospitals, you know, there's a huge amount of inefficiency of their time where they're constantly being called out on the radio because they've got leaks and they need to go and sort a leak out and then go and get a new radiator and change it because they've had, you know, pinholing failures. The bottom middle picture shows you it's a small domestic size plate heat exchanger. Some common practice now to protect new plant and equipment refurbishment, whereby it's been added onto an existing, let's say a school. They may look to use a plate heat exchanger to protect the new equipment. But of course, both sides of that plate heat exchanger need to be well protected, and we need good, clean, you know, chemically and microbiologically controlled water to pass through there. And then finally, the picture to the right-hand side is actually, it's really good to see. You may not think that, kind of counterintuitive, but that's a flushing project in London in the UK, whereby all the terminal units were in bypass. So they had flushing bypasses at the terminal units. Any sensitive equipment was bypassed before any pump was turned on. The pumps were then turned on. The velocities were increased to either 10% above the system design velocity or within something called BSRE guidelines, which is an organization called the Building Services, get this right now, Building Services Research and Information Association. And they're based out of Chicago and in the UK, and they give guidance on sort of flushing velocities you should look to achieve down set terminals, or sorry, set pipework sizes. So it's really important when the building's been designed, it's installed, before any pumps and any water's moved around that building, anything sensitive, including radiators, should be looked out. So all that initial mill scale, any corrosion deposits, and also even construction deposit. I've even seen hard hats, you know, steel toe cap boots and a pair of overalls come out of a condenser strainer once on a brand new system. Once the velocities were pushed up, we had a huge differential pressure across the strainer, and that was removed. So it's really important that we've bypassed everything. So the most important, I would actually say, yes, the most important time of system water cleanliness and water treatment is actually the very beginning. Because if we don't get all that stuff out at the very beginning, throughout the sort of facilities management life cycle of the system, it's just going to keep moving around, and it's very difficult to maintain a good level of water quality, water treatment at that point. So designing systems is really important with good flushing velocities, line size flushing velocities at terminal locations, etc. So never underestimate a good value of water treatment. So I appreciate that, if you're looking at designs, you pass it down, and ultimately the contractor, no doubt, will take responsibility for that, for the cleaning of the system. But it's really important that there's a good, hard, solid specification put into the contractor of the expectations of proving good velocity around that system, protecting terminal units, and so forth, and witnessing throughout various parts of the project. So back to basics, 4 main areas that we focus and hone in on with regards to water quality and problems is scale. So if we're in a hard water area, fresh water brings in scale minerals, and obviously under temperature they will bake on and cause problems, and not just bake on and cause problems in terms of adhering to the pipework. They will also break off, and you have these fine, if you like, very small particles that are very abrasive that are flying around the system and eventually block up small orifices. And they also prevent corrosion inhibitors from working effectively. We then get corrosion, different types of metals within the system. So you can have different types of corrosion taking place, which I'm going to get to shortly. There are different types of corrosion that can occur. We have microbiological growth, something very much now I think the industry is going to see more and more of, and again hone into, because the operating temperatures of a lot of new technologies, the higher efficiency systems, and certainly heat pump systems, etc., that run at much lower temperatures, we're going to see more issues with bacteria if it's not addressed. And then fouling and sludge, which is really essentially all of the above. There could also be contamination, as I say, from construction debris as well. So scale. So if you're in a hard water area, when it rains, that water hits the lands on the surface of the ground, depending on obviously what kind of minerals and rocks are in the ground, or minerals are below in the ground. That water will essentially absorb that and increase the conductivity and the mineral content of that water, typically calcium carbonate or phosphate. Unlike a lot of salts, a lot of minerals, if we heat them up, they like to dissolve. Scale likes to come out of solution. They likes to precipitate as well. So the only way if you're in a hard water area to really manage scale and hardness in a closed loop system is either you can look at ion exchange, which is essentially water softening. I'm not a big fan, if I'm honest. I think water softeners could also be a risk, because water softeners use salt to regenerate, and if they don't rinse properly, you can end up with a huge amount of salt or chloride levels entering your system. Or an anti-scaling treatment, which is where your inhibitors come in. So if you're using any kind of treatment, you need to make sure it's got a good level of treatment in the system to make sure that the scale will not precipitate out. And to give you an idea of looking at the United States and hard water, and depending on where your projects are, but as you can see, certainly Illinois area is very, very extremely hard, in fact, as well. So if you have got leaks, and you've got especially a heating system, and you've continually got leaks and you don't know you've got the leaks, you're not measuring that water loss on your RPZ valve, you don't know about it, you're losing, let's say, glycol inhibitor, and you're introducing hardness. What makes water more corrosive? Well, we start with oxygen. I think it's probably a well-known sort of fact. Most people understand if you've got a lot of oxygen in water, you're going to have a high level of corrosion that takes place. Low pH, so that's our acidity and alkalinity scale. 1 is, let's say, acid, as high, as concentrated as you can be, really, 1 acid, and then 14 would be alkaline or caustic, and 7 in the middle. So we generally, rule of thumb is 7. I mean, 7.2 is neutral, but we say 7 is neutral, and 7 to up to 8.5 is what we would call neutral in the water treatment industry. So if you've got aluminum, any kind of aluminum in the system, you want to be neutral pH. But alkaline isn't an issue thereafter, but anything sub 7, we class as low pH, and that will drive corrosion. Higher temperature, all chemical reactions do increase with temperature. So it's normally why you find a lot more of this black magnetite in a heating system versus a cooling chilled water system. You'll probably find you'll pull more biofilm and a lower level of iron from that system. Aggressive ions as well. So, chloride, for example, as I mentioned before, and that can even come from the mains water, depending on, what sort of treatment regime the local authority is adding to the water, particularly if they've maybe had a bad count of bacteria. And then debris in suspended or settable solids. So that's your sludge. it could be biofilm where you've had bacteria, and it could be scale. Those things essentially are very corrosive to the system. And then velocity makes water more corrosive. So as I mentioned earlier, if it's low, we're asking things to settle out or inviting things to settle out. And if it's high, we can start to cause erosion around the system. So if we want to control corrosion, we must interfere with the corrosion cell. So either we remove the water, which we can't do, it's a hydronic system, reduce the amount of oxygen that is in our reach. So we can use various types of mechanical means. We can use air separation, which removes free air or microbubbles. And if we want to remove dissolved oxygen from the water, we can use pressure step degassers, which essentially use Henry's law. They take a small volume of water at a time, reduce the pressure. The dissolved oxygen is put back into, it comes out of solution and released out of an air vent, and then that water's pumped back in the system. You see those typically certainly in the UK on district heating networks. We need to stop the oxygen getting to the metal as well. So really that's where your corrosion inhibitors do their job. They lay a microscopic film to stop that happening, or stop the metal going into solution altogether. And that could be down to, types of materials that are available. And we need to manage settleable and suspended fouling. So through filtration, really, ultimately, it's very important that we have the right amount of filtration in our system. So if we start, so I covered off scale, really, and then talked about what makes water more corrosive. So let's talk about corrosion. There are actually different types of corrosion that we need to be aware of. But first and foremost, we can't stop corrosion. That's just not correct. It wouldn't be a technically correct statement. We can only slow it, or we can only control it. And that's really what we're going to cover off as we go through this. So all metals will want to go back to, their sort of natural state, chemically stable form, whether it's oxide, hydroxide, or sulfide. So closed loop, we've got a lot of pipe work in buildings. We need to manage protecting that both, not just internally, but also externally as well. So particularly if you've got pipe work that's exposed outside within the elements as well. So in terms of corrosion, you've got iron corrosion. So what some people refer to as rusting. And it's really where the metals of the iron lose electrons to form iron ions. And it takes place in the presence of oxygen and water. So it is accelerated at high pH, acidic pH, low pH, should I say, and certainly under higher temperatures. Now, you may think, well, hang on, what makes my system, what will give the water, make it low pH? Where would the acid come from? And that can really be through either carbon dioxide, or it can actually be from, and in most cases, it comes from bacteria. If you've had a bacterial problem, maybe the system's been shut down all summer and you turn it on, areas of the system may have bacteria that will produce acid, so that could increase that. If you are using plastic pipework within your system, we want to again prevent oxygen from entering the system. There has been in the UK, I'm not so sure of any, I've not heard of any stories, anecdotal stories in the US, but if you are using any kind of plastic in your system, certainly pipework, just make sure it's of the oxygen barrier type. We had for years, there was an issue here in the UK where pipework was allowing oxygen in through the pipe wall, and then radiators were lasting literally a matter of months. You can use pH, so alkaline pH is a way of controlling corrosion. So long as you don't have aluminum, you could actually operate pH anywhere between sort of 9.2, which is perfect, but certainly sub 10.5. And managing just pH alone will assist with controlling corrosion to some degree. But it's not suitable for all metals, as I say. For aluminum, anything over 8.5, and you're going to start to cause corrosion, and you're going to start causing problems really for any boilers if they are aluminum. And copper as well. If you're using copper in a system, you don't really want to be going above 9.2 in any case. So if you don't control, if it's uncontrolled, we call it corrosion. And the word passivated refers to when the system is under control. And we talk about passivating using inhibitors. I'm going to just show you here the Galvanic Series. And the reason I'm showing you this is for, there's something called galvanic corrosion you may or may not have heard of. It's very unlikely that we find nowadays systems that have, all the same metals throughout the system. A lot of old installations going back many years And even I was working with a client who's got a system that's 100 years old, believe it or not, or the pipework is at least, you know, and everything is mild steel. But very rarely you're going to find systems now that don't have mixed metals throughout the system. So the further apart on the galvanic series these metals are, the more reactive they're going to be. And one is going to act as the cathode, or it's least active, and the anode is the most active. And then we're going to see a rapid level of corrosion. So the next slide I'm going to show you sort of paints that picture ultimately. If we're connecting and we're looking to connect any pieces of metal that are dissimilar in any way, we need to ensure within any specification that the contractor uses appropriate jointing compounds or jointing couplings to prevent this from happening. But for it to happen, for us to have galvanic corrosion, we need those two different types of metals located together and then in an electrolytic solution, which is the water. So we need dissimilar metals. We need them to have electrical contact with each other. So let's, for example, say in the picture that we're seeing here, that they were, you know, a coupling was used. However, if we've got dirt and debris or corrosion deposit that starts to settle out, it almost acts as an electrical contact over the two pieces, and then we can start seeing localized galvanic corrosion. So it's only going to happen in the pipework. You can have flanges, you know, connecting pipework and bolts going through it. That doesn't give you the same concern because there's not an electrolyte, you know, within that. It's within the pipework itself. So that's, as I say, galvanic corrosion. General corrosion is pretty much what it says on the tin. It's a main surface area, you know, of a metal, and it's over the entire surface. Something that's very easy using corrosion coupons. We can actually measure the losses, metal losses in a system. But it's you know, it's not the most serious. As I say, it's fairly straightforward to predict and action. Aluminum corrosion cell, really, as I say, aluminum is affected by pH. So if you start getting alkaline pH, most commonly when we see aluminum corrosion, it's usually in a closed loop system. It's usually the wrong inhibitor or incompatible inhibitor that's been added to that system, which has caused the problem. A lot of water treatment companies will, you know, unfortunately assume, oh, you know, I can use my inhibitor on all my sites that I'm looking after, and they put it into a system that has aluminum heat exchangers or any kind of materials. And, you know, the higher pH or alkaline inhibitors run at about 9 to 10. So, of course, we can start seeing problems. Pitting corrosion. So we have a small hole or, you know, a pit that forms in the metal surface itself. Usually we've not had a good level of inhibitor laid down. So it could be that you haven't monitored, or the site hasn't monitored the inhibitor levels. They're not maintaining optimum inhibitor levels. It could be that the pipework basically isn't very clean, or it could be biofilm that's laid down as well. So the area becomes anodic at that location, whilst the remainder becomes cathodic. So you need to be free of debris and biofilm, and certainly, as I say, a consistent level of inhibitor. Under deposit corrosion, really, as you see here, that could be a combination of corrosion, scale, or even biofilm, and it's similar to the pitting, you know, in crevice. It's really about the concentration of chlorides in the void. So what we have is where you have a high level of oxygen through the water that's passing over and a lower level of oxygen beneath, that will drive the corrosion cell essentially, and at the same time that will increase the if you like, the level of chlorides, for example, in this particular case, that could cause corrosion. And you'll see here as well that you know, radiators is a very, very common form of under deposit corrosion, as one would expect. We may see that on pipework as well. If you've got lateral runs of pipework, or you know, horizontal runs, you might see pinholing as well from under deposit corrosion. But it's usually where higher volumes of deposits settle out, which is normally radiators, or it could be a vessel of some sort. So it's really important that we maintain the flow velocities correctly. Crevice corrosion. This photograph here is actually a lot of the press fit, sort of common, very popular now is the rise of press fit pipework, crimped pipework. This is mild steel, thin-walled mild steel. So you can see it has well, you may not tell, but it has a rubber seal which has been crimped. Now, no issue with the installation. I think it's more a manufacturing defect. When that pipe has been pushed into the joint, there's a huge crevice that's been left there, and that leaves a pocket of stagnant water. And again, similar to the other corrosions we've discussed, whereby you've got different levels of oxygen, and obviously no treatment can get access to there either. So you have this crevice corrosion occurring. Can look actually sometimes worse than that. Sometimes you can have flanges that will fail, where flange joints haven't been put together, sort of, if you like, equally. Erosion, corrosion, so too much flow or high levels of suspended solids. Either is really erosive, too much velocity, or too much in terms of suspended solids, like shot blasting down the pipework. So again, good filtration is required, and at the same time, making sure that we aren't over-egging our flow rates, making sure our flow rate design around our system is accurate enough and within ASHRAE guidelines to support velocities through the system. Not too low, not too low on velocity to let things settle out, but certainly not too fast either. And then there's cavitation, bit of a sort of anomaly. It's a form of erosion corrosion. So we have a formation and a collapse of vapor bubbles, and it's really during a change in the fluid pressure, typically adjacent to the surface. I'll give you some examples where you may see this. This particular picture is a control valve. You can hear this on pumps, in fact. If you go into a plant room and you hear a pump, one, it sounds very high pitched. It's running well above its curve, and it's struggling to draw, therefore, the right amount of water it needs to satisfy the pump curve. We can start seeing a pressure drop near or just upstream from the pump suction impeller, and we get these vapor bubbles occurring, and then you see sort of like vortex of bubbles occurring right near the impeller, and it literally sounds like a bag of nails has been thrown in behind that pump almost. It could even be your strainers. You may have a blocked strainer, a dirty strainer at the pump. It's almost like closing back on the valve that serves that pump. So many types of corrosion. Another one is stress corrosion cracking. It's a form of corrosion. So typically we see this with bridges that suddenly collapse. But within a closed loop system, you would normally see this either in maybe a boiler failure, typically a stainless steel boiler. Perhaps you've seen a corrosion cracking occur, or probably going back a little while now, but non-DZR, dezinkification resistant brass fittings would crack. And for that to happen, you need three things really, all in unison. You need a tensile stress, susceptible material, and a corrosive environment. So a tensile stress is our system, it's under pressure. So the material is under pressure. A susceptible material, so let's say in this case, a non-DZR brass, and then we have a corrosive environment. So to give an example, this might be a chilled water system. We've had a bacterial problem, wasn't picked up, and the bacteria, amongst producing gas, which you might think is air, and producing acids, which drive down the pH, they can also produce other sort of chemicals as byproducts, one being ammonia. So in this particular case, the ammonia is the corrosive environment against the susceptible material, which is non-DZR brass. And what that does is it strips out the zinc from the brass and leaves really a porous copper, and then we see this cracking. So again, this is where normally you see, certainly on chilled water systems, most people use a bronze, specified bronze for chilled water systems, because it's typically more on the chilled water systems you're going to see this. And then one that normally is overlooked, believe it or not, is bacteria. Bacteria is a form of corrosion, something we call microbiological influence corrosion, MIC. So it's either direct, so it's the action of the bacteria, underneath, for example, a biofilm, a slime, something called sulfate reducing bacteria that produce acids. They are anaerobic as well, so they don't need a huge amount of presence of oxygen to survive. And then there's the production of biofilm itself. So a bacteria, to create its colony, would create like a biofilm. This is like a slime, presence of a slime, like a kind of best way to describe, like an enzyme produces that protects it. It creates its habitat, it allows it to survive and flourish. But that biofilm, that slime, lays on the pipework surface, and as a result, your inhibitor can't get to the surface to protect it, and underneath is your bacteria munching away at your pipework. Sometimes iron bacteria that will literally eat the iron pipework. And of course, your inhibitors, I say, your inhibitor cannot get to the metal surface, and therefore you start having corrosion on that point where there is inhibitor and where there isn't. So we need to look out for bacteria. This is some thin-walled pipework from the UK, but what looks like Swiss cheese, just to give you an idea what the bacteria have done to that piece of pipework. And then there's indirect. So I was at a school or a college in Maine, in the state of Maine, and this was going back probably about 3 or 4 years. And I listened to the problems that people have before I can sort of understand what I think the root cause is. And they were saying that they don't really have too many problems apart from come the fall, when they turn the system on and fire everything up, and then they have poor water quality, pump seal failures, and all their inhibitor that they topped up, in just before they closed down, sort of round about spring, it's all gone. They don't know where the inhibitor's gone. They've not had any water leaks, and that's straight away. The question I asked was what inhibitor were they using, and they were using something called sodium nitrite. That's a food source for bacteria. Once they told me that, straight away I thought to myself, you've had a bug problem. You shut the system down all summer, and then you've had a bug problem, and that's basically eaten all of your inhibitor, produced plenty of acids and biofilm, and so forth. And then of course you turn your pumps on, and you've got a rapid increase in the level of corrosion in your system taking place, more corrosion deposits, and of course whatever's been created during that period of time during the shutdown is now causing corrosion as well. But just to give you an idea, and it's a pretty disgusting picture, this is actually from a military base in upstate New York. This is one of our X-Pot compact filters. It's a cartridge filter underneath all that, would you believe? And that's biofilm. So this is the slime that I was talking about. We've removed this using a non-flush cleansing agent, which strips the biofilm, and we killed the bacteria through pasteurization in this particular case. But yeah, so this stuff's lurking in the system, and this is what happens when we don't monitor for bacteria, and the temperatures are, let's say, at the right levels to support bacterial growth and proliferation. There are different types of inhibitors. Don't expect we need to know all of these, but just be aware there are different types of inhibitors that do various roles to protect different metals in the system. So you'll have all kinds of blends of products out there available. But just because someone says it's inhibitor and you can, it's great, it's an inhibitor, I do recommend that if you can specify a product, it should at least have NSF approval. So whether that's a glycol or, an inhibited glycol, some form of kite mark that says it's been independently verified. Something that may make you laugh in the UK, I remember coming across a farmer. If you can sort of sell a technical solution to a farmer, you're doing really well. They're probably one of the most challenging in the UK, at least. And he said, no, I can get my inhibitor from this chap down the road, and I can have it whatever color I like. So he was more concerned about the color rather than what was in it. So it is really important, I'd say in terms of specification and for the life cycle of your system, just be sure you're setting some boundaries with regards to water treatment, that you want products in there that are, do what they say on the tin, as it were. And then we have biocides. So we talked about inhibitor to control corrosion and fouling, but then we have biocides. And a biocide, think of it, it's an antibiotic. Okay, so if we're filling a system up for the first time, we really probably want to be adding a biocide to the system. Mains water that we drink, municipal water that we drink, generally has low levels of bacteria, nothing hopefully pathogenic, but under stagnant conditions, they grow at a logarithmic rate, and they create these biofilms. So treating the water before it comes in, and certainly monitoring, that prevents the buildup of these biofilms as well, because biofilm will protect bacteria from biocides. So if you are using a biocide on an existing system, you need to think about pulling that biofilm out that you saw on the photograph earlier. So you need some form of biodispersant. So it's ensuring that any water treatment specialist or contractor specialist, within their methodology statement, and say, for example, you've got an old school with new plant, but you want to clean up the old system, it's important that you tackle the bacteria, you tackle the biocide with something to strip the biofilm, something to strip that biofilm as well, and then something to kill it. Antifreeze or glycols, as they're known, there are two types typically used. So there's monoethylene, or MEG, as it's known for short. Monoethylene glycol is really the most, first of all, I would say it's the most readily available, although glycol at the moment is very difficult to come by. Prices are changing due to the market conditions, but MEG is the most commonly used one. It's more, I would say, competitive than propylene, but it is toxic. So if you're looking to be environmentally friendly, I would certainly propose not to use that and specify monopropylene glycol. This is a food source type of glycol. So it is a bit more expensive. It doesn't have quite the same level of freeze protection, but it gives you peace of mind on your site, on your project, your design. If you are specifying what's in your system, any kind of glycol, I would certainly recommend it's monopropylene. So if you do have leaks or drain downs, you're not trying to worry about effluent discharges or certainly a toxic product getting into the aquifer below. Typically used in closed loop systems. Not all glycols, by the way, come with inhibitor. So some people make the assumption that I've got glycol, therefore I've got inhibitor. They don't all come with inhibitor. So it's important to make sure that if you're using a glycol, it's it's got an inhibitor, it's being used in conjunction with an inhibitor that carries some form of a kite mark. Very simple to test with something called a refractometer. But going back to bugs, and this time mixing it up with glycol. So glycol itself is great. So anything above 25% in industry is deemed to be a biostatic. Bacteria cannot flourish above 25%. Now in North America, typically you dose well above that, so shouldn't be an issue, right? However, if you've had a leak and you're not aware that you've had that leak on that system, you could be losing that. And once you go below 25%, concentration of glycol or volume of glycol in your system, you could start feeding that bacteria. It becomes a food source for the bacteria. So you may have a chill water system or even a heating system, and you think, where's my glycol gone? I've lost it. Well, combination of leaks and then combination of bug problems. You think you've got air in the system, you can't get rid of it. You're losing glycol. You could actually find that you've got glycolic acid being produced. The bugs are now eating it, producing glycolic acid. And as I say, what do we have with acid or acidic conditions sub 7? We start having problems with increase with corrosion. So maintaining above 25% glycol is really important. And as we look to be more energy efficient and we want to clean up our systems, or we want to maintain new systems in a good condition, having a good level of water quality is important. But if we do get biofilm, it's actually more of a thermal insulator, as it were, than scale. So the last thing we want is scale, but even if we're not in a hard water area, the last thing we want is biofilm at the same time, for the reasons I alluded to before in terms of erosion, corrosion for a start, and it's affecting inhibitor regimes, but also for energy performance. So sorry, I'll just take a sip of tea. And of course, so what we do then is we want to think about, these are the catalysts. I've gone through really the catalysts and kind of how these things all interconnect within a system. But what does that actually mean, kind of, what we see every day, or if we're involved in a project? So just going to touch base on some slides that cover management and litigation. So good management should lead to the avoidance of litigation. And a closed system management should really be approached like a Legionella management process. So it needs responsible people detailed for the project and beyond. A communication or management pathway. So that becomes from whether it be, right at the beginning. I think water treatment contractors should be involved at the design stage. I think leaving it that they fall directly under a contractor themselves. I think there needs to be a closer connect. In the UK, we have something called soft landings, and it's very much about that cradle to grave, but that communication and that coming together from everybody at the beginning of the project. So input from everybody. So communication is very, very key. Clear management pathway. We want a written scheme documented. Cover the types of metals on the system and the operating characteristics. So again, that avoids us putting the wrong chemicals in the system. Water chemistry, multi-metal inhibitors, so really covering all metals and pH neutral, mitigate risk. We need to identify any risks. So that can be down to a controls philosophy that could lead to stagnant conditions of the system, for example. A treatment program, and of course, good record keeping. And nowadays as well, with everything on the cloud, a lot of data now, there's no reason why it shouldn't be inputted into it's like an Excel spreadsheet that then produces graphs. Water treatment is very much about science. Science is very much about trends. So if you're measuring levels of iron dissolved or total iron or copper, you can see and track, do we have an increasing trend? So that's really important. I mentioned existing systems. It's really one of the most problematic and contentious scenarios. So, generally you're never going to have a good an existing system that it's not going to be perfect. It's not going to be in a good condition. And yet you're adding new plant and equipment to it. Okay. So you just need to be mindful of that. And so some contractors may insist on having new system water quality in existing system from a warranty point of view. Well, how do you do that if you've got a very old, 20-year-old system, new boilers going in, no plate heat exchanger, no hydraulic separation? How do you manage that? How can you offer that level of warranty? It becomes challenging. And I think it's about managing expectations from the get-go, really. It's normally impossible to achieve. So it's investigate the existing systems early, discuss and agree acceptable water quality early on. I mean, our solutions, typically we tell to clients, if you've got old systems and you're adding new plant, to be honest, putting our sort of ex-pot products on, 3 months before, use that existing equipment, boilers, pumps, almost sacrificially, to clean up that system well before you look to add anything new. Basically make a head start, because there may be increased risk for the owner or the managing agent they need to be aware of. So again, plate heat exchangers are quite common, but you do need to add more energy into a plate to meet the same heat demand. So not necessarily when we're trying to design for energy efficiency. So designing for water quality, it's in an ideal world, we'll have flow rates above sedimentation velocity, constructed from corrosion-proof material, and of course filled with sterile water with no contamination or nutrients for bacteria. There'll be line-size flushing loops at terminal units everywhere. But the reality is we sometimes have poor design. I'm not suggesting anyone online is you're going to design a system poorly, but in reality, sometimes there are poorly designed systems or they're poorly commissioned. And that's really important. The commissioning phase is absolutely vital, and the commissioning engineers should pick up, or commissioning technicians should pick up if there's anything that needs to be changed. They should be coming on site with the water treatment company, the commissioning team, even before the water treatment company make a start. Mixed metals and delicate metals are typically used on a system, and sometimes you can have poor water quality used. So it might be used from a mains water supply onto a project, onto a construction site that it's not being used. Somebody's tapped into a hydrant or something, and that's been sitting there as a dead leg for some time. And of course, construction debris, mill scale rust, fluxes, and so forth. And again, as I alluded to before about inhibitors, some inhibitors will actually act as a food source for bacteria. So selection and choice of the wrong types of treatment, not just for the metals, but also for whether or not we're increasing the risk of bacteria. So that can be the reality that we see. So, design needs to keep as much of A and mitigate B, essentially. We want to avoid dead legs, stagnation. Consider stagnation a bit of a killer, to be dramatic, but to drive the message home. Stagnation and dead legs are really not a good place, or don't have a place on a closed loop system. So thinking about that design when a control valve operates, or if there's in terms of controls philosophy, we need to ensure that we keep water moving, essentially. So minimum 1 hour every 24 hours. You want all that water moving and actuating valves and so on. If we don't need heating or cooling, then of course we can look to not run the boilers or run the chillers, but wherever you can, just keep water moving. And as a minimum, typically BSRIA, as I say, based out of Chicago, they do provide guidance on this. They have some great documentation they provide for engineers, but keep water moving. Think about treatment before you even think about filling, and make sure the fill water is of suitable quality. So you may not always treat before you fill, but even as a basic, just take some samples of what the water looks like you're filling with. Add biocide and inhibitor with first fill water. Certainly don't drain after the pressure test. Worst thing you can do. I came across a client that was actually draining a chilled system in the winter, and they were saying, but we always get problems once we've refilled the system. Come the summer, we've always got water quality issues. And I found that, I know I'm sort of from a water treatment background, but I thought that was rather bizarre that they wondered why. Don't delay between pressure test and pre-commission cleaning, and then no delay between pre-commission cleaning and that practical completion. So essentially design the whole program accordingly, right from start to finish, making sure that's designed all the way through. In terms of avoiding common contaminants, installation debris, as I mentioned before. So, I mean, even welding rods, a lot of things nowadays are prefabricated and a bit off site, but I have come across Coke cans that have been put in by, I guess, disgruntled employees. Hard hats, as I say, a project in Paris where I think we found everything but the body. So that could be sabotage. Ping pong balls, polystyrene and chemicals. So I've never come across ping pong balls, but colleagues in the industry have. And you think you've got a blockage, you work out where it is. Of course, you drain down, the ping pong ball has moved. So there are all sorts of things that can even happen at construction phase. So just to recap, corrosion products are oxides of iron forming in steel pipes in the presence of water and oxygen. We have other copper corrosion and so forth. Actually, I didn't touch on copper corrosion. Biological fouling as well. I'm running a bit short of time, so I'm just going to fly through some of these. But
yeah, Darren, just want to let you know that about 8 minutes left or so.
Great, thank you. I'm just coming towards the end. So, pre-commission cleaning, essentially. Oh, just come back here quickly. So for pre-commission cleaning and so forth, so we need to make sure that in the methodology, we're covering anything from flushing, velocities, any chemicals that we're going to be using really, and certainly maintenance thereafter. If you, in terms of pre-commission cleaning, velocities are key. So any witnessing and reviewing method statements and making sure any sampling was taken. If it hasn't been done properly, have we done it again? So just to avoid problems, fill and pressure test. First fill and pressure test, think about treatment, essentially all the way through the program. And just to recap again, daily circulation, think about the BMS controls. And I think I'm pretty much touched on that. Temporary flushing bypasses should have been removed. So this image here, the schematic, shows a flushing bypass at a fan core unit. So we'd recommend, a line size flushing bypass, say, for example. Once all the initial velocity has been put through the system and the system's all cleaned, that would be closed, and then you would open up to the unit. So I think I'm kind of echoing what I've touched on there. So I think just in summary, in fact, I'll jump straight to this due to time. Keep in perspective. I think this one hits it home really. Think of an engine in our car. If you have a car, if we don't service the car, we don't change the oil, we're not going to get the miles out of that engine. We're going to have head gasket or big end bearings going on us. We're going to have basically a car that is not reliable. So we know that we need to maintain and service the car regularly. Think of that with a closed loop system. Good level of water quality, good level of treatment, good level of filtration. That's it from me. Thank you very much. I'll now open up to any questions.
Great, thanks, Darren. So we did have one come through from Marvin. For variable flow systems, where can we experience low velocities during extended periods of time due to seasonal variation in loads? Do you know any systems that schedule via overrides high flow rates on a scheduled basis as a means of removing deposited sediment in conjunction with filtration systems to remove sediments?
Yeah, that's a great question. The answer is, in most cases, no, people don't. More so now on sort of newer projects. And certainly, and I know I'm talking from the UK here. I would say that, I would say no is the answer. Not many other than new projects and new designs now. It's now the problems that are occurring that we're seeing. People are becoming more aware of it. So you're seeing it more on new project installations, essentially, I suppose, or where we're having refurbishment works done. It's just getting the message out there, quite frankly.
Let's see. I haven't seen any other questions come through. We have a few more minutes, so we'll see if anyone has anything else that they'd like to get answered. In the meantime, again, thanks, Darren, for presenting and taking the time. Everybody, there's a survey at the end, so please take the survey when you close out of the webinar, and hopefully you'll all be able to register and check out the remaining webinars we have for the spring conference.
Thank you, and Randy, as I say, thank you ever so much for inviting me along, and to all your fellow members and other attendees, this evening. It's been an absolute pleasure to be invited along, and hopefully that was provided some insight as well. So yeah, thank you.
Yes, it was very insightful. Definitely went into good detail. And and just in case some people didn't see, someone asked about the PDH certificates. Those will be sent out to your email addresses that you registered with to all attendees. So just a heads up there. And then there's also going to be a recording available on the ASHRAE sites. I put the link into the Q&A section, so you'll be able to find that there as well.
Fantastic.
Okay. Don't see any other questions coming through, so I think with that, then we can call it there. Thanks again.
Great.
Thanks again for everyone for coming, and thanks again, Darren, for taking the time.
More than welcome. Thank you again. Take care, everybody.
Have a good one, everyone.
See you.